Hello friends. So today we are going to solve the questions from Heat and Thermodynamics. So these questions are from the year 1982. Two questions. 1983, one question, and 1984, also one questions. So total we are going to solve 4 questions. So the first question, it was asked in the year 1982, and it states that calculate the work done when 1 mole of perfect gas is compressed adiabatically. The initial pressure and the volume of the gas are 10⁵ Newton per meter square and 6 liter respectively. The final volume of the gas is 2 liters. Molar specific heat of the gas at constant volume is 3R/2. So we have to find out the work done for 1 mole of perfect gas when it is compressed adiabatically. Okay. So it means that first of all the process is adiabatic. We have a adiabatic process, which means no heat is exchanged. No heat is exchanged, or Q is equal to 0. Therefore, from first law of thermodynamics, from first law of thermodynamics, we can say our delta of U will be equal to negative of W, where W is our, you can say, the work done. And the various parameters that are given to us, we are given the number of moles, that is value of N is equal to 1. We have initial pressure, initial pressure is our P1, is our 10⁵ pascals. We have our initial volume, and initial volume is our V1, which is our 6 liters. So we can write it as 6 into 10⁻³ meter cube. We are also given final volume, that is our V2, that is our 2 liters. So 2 into 10⁻³ meter cube. And we are given specific heat for a constant volume, that is CV is given to us. So we can say our CV is given to us as 3R/2. Okay. and we have to find out the work done. Okay. So first of all, we are going to find out the adiabatic index. Adiabatic index, and we can say that for a perfect gas, the standard relationship, we know that our Cp is equal to Cv plus R. So therefore, from here we can write our Cp will be equal to Cv is given to us as 3R by 2 plus R, giving us 5R by 2. And we know that our adiabatic index, which is represented as gamma, is the ratio of our Cp by Cv. So we substitute it, get 5R by 2, and this comes as 3R by 2. So here R by 2 and R by 2 cancels out, and we get this as 5 by 3, which will be approximately equal to 1.667. Now we are going to find out, or we can say, the adiabatic process, the relationship between pressure and volume. So we can say that initial and final state, initial and final state using adiabatic process, adiabatic condition. Adiabatic condition, and that is a standard formula. We know that P multiply V raised to power gamma is equal to constant. From here we can say P1 V1 gamma is equal to P2 V2 gamma, and we need to find out our P2. Therefore we can say that our P2 will be equal to P1 V1 upon V2 whole raised to power gamma, and we substitute the value. We get this as P1 is our 10⁵, and V1 is our 6 into 10⁻⁻3, V2 is 2 into 10⁻⁻3, and gamma V is our 5 by 3. So this comes as our -3 minus cancel, 6 goes by 3. So this will be equal to our 3 raised to power 5 by 3 multiplied by 10⁵. Therefore we can say that our P2 will be equal to 6.24 into 10⁵ pascals. Now we have to find out the temperature, we have to find out work done. Okay, and now we are going to find out the temperature, and then we are going to find out the work done. Okay, because from there we are going to find out a delta U, and in order to delta U we need the delta T. Therefore we can use the ideal gas law, that is equal to PV is equal to nRT, in order to find out the temperature. So we can say ideal gas law. This gives us that PV is equal to nRT, and we can divide this ideal gas law into final as well as initial condition. So we can say our initial state and initial state, we can write this as T1 is equal to P1 V1 divided by NR. This comes as 10 to the power 5, 6 into 10 to the power minus 3, N is 1, and our universal gas constant is 8.314. So this comes approximately equal to 72.12 Kelvin. We come to the final state. Final state, that's a T2 will equal to P2 V2 N times R. So we get this as 6.24 into 10 to the power 5, 2 into 10 to the power minus 3, and N1, and this comes 8.314. This approximately equal to 150.01 Kelvin. Okay. So we got our T1 and T2. Or we can also, in place, if you don't want to use this ideal gas law, we can also use the adiabatic temperature volume relationship. Okay. If you want to use, you can use adiabatic temperature volume, which gives us that TV gamma minus 1 is equal to constant. Okay. So here also we can find out our T2, okay, because T1 we already found out. Okay. So this can also be used, because T1 we have to find out our ideal gas law, then we can use this adiabatic process, a temperature volume relationship, to find out our T2, but answer will be coming same. Now we can find out our finally, that is our work done. So we can say our work done, like we said initially, that for adiabatic value of Q is equal to 0. So this gives us that our delta of U is equal to negative of W. We can find out this change in internal energy, that is delta U. We can say that change in internal energy, that is our delta U, will be equal to N CV delta T. Delta T is T2 minus T1. Therefore we get delta of U is equal to N is 1, CV is our 3R by 2, and delta T is T2 minus T1, which comes as our 150.01 minus 72.12. So we get this delta U will be approximately equal to 971.37 joules. But we have to remember that the gas is compressed. Okay, so it means if gas is compressed, the work done is on the gas. So you can say, since gas is compressed, therefore work is done on the gas. Work is done on the gas. So based on this, we can say that the work done on the gas will be our positive. And thus we can write that work done by the gas will be equal to our, and this is 971.37 joules. One second. Calculate the work done when 1 mole of the perfect gas is compressed adiabatically. Okay. So, in this case, there are two things in the first line itself. It states that calculate the work done when 1 mole of perfect gas is compressed adiabatically. Okay. So, the compression means the work done will be on the gas. Okay. But we have to find out the work done by the gas. So, that's why the work done by the gas will be coming as negative. Okay, so we have to keep this thing in mind. And if we do not want to use this process, we can also use that our work done is equal to our P2V2 minus P1V1 divided by gamma minus 1. Okay. This also is going to result in the same answer. Okay. We can use the work done is equal to P2V2. This is also called as a work integral. This is called as a work integral. So if you can use this formula, or we can use from the first law of thermodynamics. Okay. Next question. It was also asked in the year 1982, and it states that a solid sphere of copper of radius r and a hollow sphere of the same material of inner radius small r and outer radius capital R are heated to the same temperature and allowed to cool in the same environment. Which of them starts cooling faster? So in this case, we have two spheres, one is hollow and other one is solid, and they are of same material. You can say both spheres they are made of same material, so they are going to have same materialistic property. It means their density will be same and their specific heat will be also same, and also their emissivity will be also same. Okay. So these are the three key properties. For both the spheres it will be same. Okay. And secondly, it is said they are heated to the same initial temperature and cool in the same environment. So it means the temperature difference between each sphere and the environment is identical at the start. So you can say that the temperature difference between heat sphere and environment is identical at start. Okay, so you have to remember everything will be same at start. Okay. And okay, next few things, if they come to the picture, we can discuss them later on also. So for the cooling process, we have to keep in mind that there is a law which is called as a Newton's law of cooling. Newton's law of cooling, and this gives us that the rate of heat loss, rate of heat loss means dq by dt will be equal to minus h times a, and we have this is T minus T naught, where h is our heat transfer coefficient. H is our heat transfer coefficient. A is our surface area, and T is the sphere temperature, and T naught is the environment temperature. T is our surface sphere's temperature, and finally T naught is our environment temperature. And there is another law which is also called as Stephens-Boltzmann law, which defines as heat loss rate in terms of the radiation. So we can say for a radiation heat loss rate, and it is our Stephens law. It is also called as Stephens-Boltzmann law. Boltzmann law, and this gives us that dq by dt is equal to minus epsilon sigma a t raised to power 4 minus t raised not raised to power 4, and here this epsilon is called as emissivity, and this sigma, it is called as a Stephen-Boltzmann constant. And if we see the given condition, from there we can say that they are made of same material, so the emissivity will be same. Boltzmann law is also constant, and the initial temperature, that is this T minus T naught, will be same for both. It means this heat loss rate is dependent upon the surface area. So from here we can draw a conclusion that our heat loss rate is dependent on A, which is our surface area. So let's calculate their surface areas. surface areas. So first is our solid sphere. Solid sphere radius is given as A. So we can say the surface area of the solid is equal to 4 pi r square. And the hollow sphere, okay, in case of this hollow sphere, we have to remember that only the outer surface radiates to the environment. So this hollow sphere, you have to remember that only outer surface radiates to environment. Therefore, we can say that our A of hollow will be equal to 4 pi r square. So it means their surface areas are also identical. Therefore, the heat loss rate is same for both the sphere at the initial temperature. So from here we can draw the conclusion that surface area are identical so heat loss rate that is dq by dt is same for both spheres at initial temperature. At initial temperature. Okay. Now let's find you can say write the relationship which relates the heat loss due to temperature change. We can say heat loss due to temperature change, and this is a standard relationship that our dq by dt is equal to minus mc dt by dt. Mean rate of heat loss is product of the mass, specific heat and rate of change of temperature. Okay. And if we rearrange this equation, we can say that our minus rate of change of temperature will be equal to dq by dt divided by mc. And for radiation heat of loss, we can say for radiation we can write that minus dt upon T is equal to, this will become epsilon sigma A, and this comes as T raised to power 4 minus T naught raised to power 4 divided by MC. And here everything is constant except our area and the mass. So we can say that our minus dt upon T is proportional to area upon mass. Okay. So ultimately, from here we can say that the ratio, this area to mass ratio, is going to define how fast the body is going to cool. Higher is the surface to area mass ratio, faster will be the cooling. Okay. This relationship, this conclusion can be drawn from here. Okay. So you can say higher surface area to mass ratio, faster is cooling, or we can say cools faster initially. So let's find out the, you can say, the masses, because area we have already calculated. So you can say for solid sphere, we have volume of the solid sphere will be equal to 4 by 3 pi r cube, and mass will be equal to density multiplied by volume of the solid sphere, and which we can write will be density multiplied by 4 by 3 pi r cube. Now we come to the hollow sphere. Hollow sphere, the volume of our hollow will be equal to 4 by 3, and this comes as outer radius minus inner radius, and from here we can write our the mass will be equal to, this is mass of solid and this is mass of hollow. Will be equal to density volume of hollow which will be equal to rho 4 by 3 pi r, and this comes as r cube minus small r cube. And so if you make the comparison between the mass of the solid and mass of the hollow, we can say that our mass of hollow will be less than mass of the solid. This we can just directly write from here. And let's find out their ratio now. So we can say our surface to area mass ratio, surface area to mass ratio and we get for solid sphere we get area of solid and mass of solid, and this comes as a 4 pi r square, and this comes as sigma 4 by 3 pi r cube, and this comes as 3 upon rho times r. And we come to the hollow sphere now. Hollow sphere, area of hollow divided by mass of hollow. Area is same, that is 4 pi r square, and this comes sigma 4 by 3 pi r. This is r cube minus small r cube. This gives us 3 upon rho r cube minus small r cube. And now we come to the cooling rate. So we can say cooling rate of hollow and cooling rate for solid. That will be coming as 3 upon rho r cube minus small r cube, and this comes as 3 upon rho times r. This will be equal to r upon r cube minus small r cube. And like we said, here from this also we can just make a direct comparison or conclusion that our hollow sphere cools faster. This we can draw the conclusion also. Okay, if we want to write, we can still write it, but not going to help much. We can easily see that our one second. Yeah, I think this is sufficient. There is no need to go into more detail. This question was asked in the year 1983 and states that 1 gram mole of oxygen at 27 degrees centigrade and 1 atmospheric pressure is enclosed in a vessel. Assuming the moles to be moving with a VRMS, find the number of collisions per second which molecules make with 1 square meter area of the vessel wall. Part B, the vessel is next thermally insulated and moved with a constant speed V0. It is then suddenly stopped. The process results in a rise of the temperature of the gas by 1 degree centigrade. Calculate the speed V0. So let's start with part A. And for part A, we have to find out the number of molecules, number of collisions per second. Okay, so number of collisions per second. For that, we are going to find out the density because VRMS is given to us, and for density we should be knowing the volume. Okay, so we are going to start by calculating the volume. We say for part A and part A, we are going to use the ideal gas law. Ideal gas law, which gives us that PV is equal to nRT. From here we can say that the volume is equal to nRT divided by pressure, and all the parameters are known to us. So we can say the volume is equal to number of moles is 1, and this is R is 8.314 into temperature is our 300, 27 degrees centigrade, and the pressure is our 10 to the power 5 pascals, and this comes as our 0.0225 meter cube. Now we can find out the number density, or we can say number of molecules per cubic meter. We can say that number of molecules per cubic meter. And rho is equal to, this is Avogadro's number divided by the volume. Avogadro's number is our 6.022 into 10 to the power 23, and volume we found out is 0.025, and this gives us that density will be equal to, number of molecules per cubic meter will be equal to 2.414 into 10 to the power 25 meter cube inverse. Now from here we can find out that our VRMS we can easily find out. So we can say root mean square velocity, that is our VRMS, will be equal to 3RT divided by M and its square root. We already know values. This comes as 3R is our 8.314 into 300, and this is 0.032 square root. This comes as 483.56 meter per second. Now we can find out the collision rate per unit area per unit time. Collision rate per unit area per unit time, and suppose that is given as Z, so Z will be equal to our 1/4 rho times VRMS. So we simply substitute 1/4 into 2.4147 into VRMS, 10 to the power 25 into 483.56. So this gives us that our Z is equal to 2.92 into 10 to the power 27. Now we come to part B. And it is said that now the vessel is thermally insulated. So basically it is adiabatic process. So we are given that vessel is thermally insulated, or we can say adiabatic. It means no heat exchange. And we can say that as the vessel is going to have a constant speed, so the gas is going to possess a bulk kinetic energy. So we can say the gas has bulk kinetic energy due to vessel's motion. At constant speed, that is V naught. And when this is suddenly stopped, the kinetic energy is converted into internal thermal energy, which raises the temperature, which is given as 1 Kelvin. You can say when suddenly stopped, this bulk kinetic energy is converted into internal thermal energy. Internal thermal energy, raising the temperature by delta T, which is given to us as 1 Kelvin. So first of all, we are going to find out increase in internal energy because that is temperature dependent. So we can say that increase in internal energy which is our delta U, and we are given that it is a oxygen gas, so it is a diatomic, and its CV is 5/2 divided by R, 5/2 times R. So we can say that for diatomic, CV is our 5/2 times R. Therefore, we can write that our delta U is equal to N CV delta T. It comes 1 into 5/2, 8.314 times 1. This comes as 20.785 joules. Now we are going to find out bulk kinetic energy. You can say bulk kinetic energy will be equal to over half m V naught square, and this will be equal to over delta U. And from here we can say that our V naught square will be equal to 2 times delta U divided by m, giving us 2 into delta U is about 20.785 785 divided by 0.32. We got V naught is our 36.04 meter per second. So we got the velocity as well as the number of collision per second. Next question. It was asked in the year 1984, and it states that the rectangular box shown in the figure has a partition which can slide without friction along the length of the box. Initially, each of the two chambers of the box has 1 mole of monatomic ideal gas, lambda is equal to 5/3. At a pressure P0, volume V0 and temperature T0. The chamber on the left is slowly heated by electric heater. The walls of the box and the lead wires of the heater are negligible. The gas in the left chamber expands, pushing the partition until the final pressure in both the chambers becomes 243 P0/32. Determine the final temperature of the gas in each chamber. Part second, work done by the gas in the right chamber. So basic figure is something like this. And in between there is a, you can say, this partition can slide, and on the left side we are given a form of heater. Okay. This is a basic figure given to us, and initially the pressure is P0, volume V0 and temperature T0. Okay. So we have that initial condition is our P0, V0 and T0, and we are given that it is a monatomic ideal gas. So we can say for monoatomic gas, that is our gamma, which is our Cp/Cv will be equal to 5/3, and we can also write that our Cv will be equal to 3/2 times R, and our Cp will be equal to 5/2 times R. And okay, in this case we have to remember that this entire process will be adiabatic. Okay, so what happens, as the gas in the left side, as the heater supplies the energy to the left side, the partition is going to move towards the right, okay, because gas is going to expand, and the partition is our adiabatic, and so therefore we can say there will be no heat exchange between the two chambers. This is the important part here. You can say partition is adiabatic, so no heat is exchange between the two chambers, between the two chambers. And it says that this the movement of this partition continues until the pressure, the final pressure becomes in both the chambers become 243 P0 by 32. So you can say that final pressure in both the chambers, or we can say final condition, at least with respect to the pressure, that is our PF, and it is given to us as 243 P0 divided by 32. And okay, so it is basically adiabatic process, therefore we can say that the entire process is adiabatic, so Q will be equal to 0. Okay, no heat exchange, and okay, let me write in other way. Here the left chamber will be non-adiabatic, right chamber will be adiabatic because left chamber is heated. My mistake. So I can say left chamber is heated, therefore non-adiabatic, and right chamber is our adiabatic. Right chamber is adiabatic. And in this case we have to remember that the size of the box is fixed. So if the size of the box is fixed, its total volume will be fixed. Okay. So if we can say its length is L and area is A and length is of the total box, it is fixed. So obviously the total volume of the box will be fixed. Okay, so if we say that, okay, let me write it first, then we can move further. We are going to call this as box constraint. Box constraint, you can say that box has fixed total volume. Box has fixed total volume. Therefore we can say that its initial volume of each chamber will be equal to V0 area L upon 2, and you can also say total volume of the box that is a V total will be equal to left chamber and right chamber, so it is same, so this comes as 2 times V0. And now as the partition moves, as partition moves, let us suppose that volume in left chamber is V1, then volume in the right chamber will become as 2V0 minus V1. Now let us find out the relationship between pressure and volume. Relation between pressure and volume. So we are given that the final pressure is both the chamber is same. So you can say our final pressure, that is pressure in left chamber, is equal to pressure in the right chamber, and that is given to us as PF is equal to 243 times P0 divided by 32. And now let us find out the final volumes. Left chamber we have written as V1 or VL, and right chamber we have written as 2V0 minus V1. But before that, we require what will be the, you can say, I think temperature is also required, because we need to find out the work done. And for work done, we have to, or in this case, let us use the adiabatic work formula. Okay, that is going to give us this as more conveniently. We can use traditional way also. Traditional way is our that we start with our, you can say, relationship, that is equal to PV raised to power gamma is equal to constant. From there we can say P1 V1 is equal to P2 V2, and there we can calculate everything, which is the basic your adiabatic process. And from there we can find out the temperature, that is TV is equal to gamma raised to power, T multiplied by V raised to power gamma minus 1 is equal to constant. From there we can find out our temperature, or we can say, we can also use PV is equal to nRT. But let's use our standard formula, that is our adiabatic work formula. So we use adiabatic work formula, and which gives us that the work done is equal to P2 V2 minus P1 V1 gamma minus 1. Okay. And here P1 is equal to our P0, V1 is equal to our V0, and our P2 is equal to, that is given to us, that is about 243 times P0 upon 32. And V2 we require to find out. V2 we can just find out, it's not a big issue. So we start with our adiabatic process, which gives us PV raised to power gamma is equal to constant. So from here we can say that P naught V naught gamma is equal to P2 V2 gamma. Okay. And we are supposed to find out our V2, or let us find out V2 by V naught, and let's swap the. So we can say that our V2 upon V naught whole raised to power gamma is equal to P naught upon P2. And gamma is our 5/3, therefore we can say that our P2 is, this is P naught, and P2 is our 243 times P naught divided by 32. P naught and P naught cancels out, so this comes as our 32 divided by 243, and gamma is our 5/3. Therefore we can write that V2 upon V naught is equal to 32 243, and this comes as 1 upon gamma, that will be 3/5. Okay. And this gives us this will be equal to 8 upon 27. So we get our V2 is equal to 8 upon 27 times V naught. And I think that is sufficient. If you require, we can solve other things later on also. And we need gamma minus 1, so gamma minus 1 will be equal to 5/3 minus 1 is equal to 2/3. So we can write that our okay, let us calculate this individually. So we can say that our P1 V1 is equal to P naught V naught. So one second. P1 V1 P naught V naught, yeah, this is correct. Okay, and this P naught V naught is our P2 is this, and V naught, sorry, I get my P2 V2 is equal to 243 times P naught divided by 32, and this comes as 8 upon 27 times V naught, and this will be giving us 9 upon 4 times P naught V naught, and then we are left with P1 V1 product is itself equal to P naught V naught, and we can say that our P1 V1 is equal to P naught V naught. Now we can substitute that our work done will be equal to 9/4 P naught V naught minus P naught V naught, and this is about 2/3, and this comes as 5/4. So we get this as 5/4 divided by 2/3 P naught V naught, and this will be equal to our 5 by 4 multiplied by 2 by 3 by 2, giving us 15 by 8 P naught V naught. And we can use our ideal gas equation, and we can say that our P naught V naught is equal to N times R T naught. Yeah, for 1 mole R T naught. From here we get work done will be equal to 15 times 8 R times T naught. So this is our, and okay, so we have to remember that we have to find out the final temperature. Okay, I forgot to find out this one. I'll deal it later on. So work done by the gas on the right chamber. Okay, so work done will be gas on the right chamber because it will be compressed. So therefore there will be a negative sign inclusive of that. So we can say that work done on the gas. Therefore we can write W is equal to minus 15 upon 8 times R T naught. And we have to also find out our temperature, that is on our the final temperature of gas in each chamber. So we have to find out both the temperature. Therefore we can use that the final temperature we can write that our TV gamma minus 1 is equal to constant. Therefore we can write T naught V naught gamma minus 1 is equal to T2 V2 gamma minus 1. And from here we can write our T2 is equal to T naught V naught upon V2, and we have this as gamma minus 1. And V2 is our, we just found out of V2 also. V2 is our 8 upon 27 times V naught. Therefore we can write that our T2 is equal to T naught V naught, and we have this as 8 upon 27 times V naught, and we have this is 5 by 3 minus 1, that is 2 by 3. And here V naught and V naught cancels out. This comes as our T naught, and we have this as 27 upon 8 2 by 3. So we get that our T2 will be equal to 9 by 4 times T naught. Okay, and I think this is all the things we are required to find out. Temperature we found out. Okay, we also need T1, so we can just use ideal gas law. So we can say that this T2 is for right chamber. And for left chamber we can use ideal that our left chamber we can write P naught V naught is equal to NR times T naught. And so this can be written as 243 times P naught 32 V1 is equal to NR T1. So therefore our T1 is equal to 2, this is 43. 243 divided by 32 times P naught and N times R multiplied by V1 and okay, and we already know relationship between our V1 and V naught, so we can write this will be equal to our T1 is equal to 243 divided by 32 times P naught and times R, and our V1 will be equal to 46 V naught upon 27. Okay, and this n will be 1, so this n goes away. So let me write this can be written as our 243 upon 32 multiplied by 46 upon 27. This comes as P naught V naught upon R, and from here we can say P naught V naught is equal to R times T naught. Therefore we can write that our T1 will be equal to, this comes as our 207 upon 16, and P naught V naught is our R times T naught divided by R, and this R and R goes away. We get our T1 is equal to 207 upon 16 times T naught. Okay, so this is our temperature. I think temperature, final temperature in each chamber and work done by the gas. Okay. So this completes the 4 questions, and they were asked in the year 1982. From 82 we did 2 questions, 83 1 question and 84 also 1 question. So this completes all the 4 questions. Thank you.